So today we shall talk of the different types of junctions that are there in semiconductor devices. The basic idea of the junctions comes with a fusion of a p-type and n-type semiconductor leading to the formation of a p-n junction. And in a junction there is of course some equilibrium condition. We'll talk of the forward and reverse bias, and then we'll talk of a little bit on drift and diffusion, which are basically the cause of the carrier transfer in the devices. So a junction is basically a physical region where the two different materials meet. The materials can meet referred to can be a metal and a semiconductor, or it can be a p-type or n-type semiconductor. Almost every semiconductor devices have junctions, and they're used for, and these junction-based devices are used for rectification, amplification, switching, and so on. So there are different techniques of fabrication of junctions. Either a junction is grown on a semiconductor, which is very popularly used, that is called a grown junction. It can be also an come out of an alloy formation, which is called an alloyed junction. And the third approach is basically diffusion-based junction, where you diffuse one type of carriers into another type of semiconductor, leading to the formation of diffusion junction. Of these three types of junctions, the diffusion junction is most popularly used in semiconductor devices. So in a p-n junction, we typically diffuse n-type material into a p-type semiconductor, or p-type material into n-type semiconductor, and p-type or n-type semiconductor is used as a mother wafer. So the carrier transport is basically guided by the drifting of holes and electrons from n-type to p-type and vice versa. There is an absence of an external voltage under equilibrium conditions, hence there is no steady carrier transport in a p-n junction diode. After some initial migration of carriers, it goes to some equilibrium condition, and a potential drop is formed across the junction, which is called the built-in junction potential. Electrons from the n-type region near the p-n interface tend to diffuse into the p region. Electrons leave positively charged ions into the n region, where the positive charged ions are the donor ions. Similarly, the holes from the p-type region near the p-n interface begins to diffuse into the n-type region, and the negatively charged ions or the negatively charged acceptor ions are left behind. So as a result of the this migration of electrons and holes, the p-n interfaces lose their neutrality and becomes charged, and this charged region is called space charge region or depletion region. So this is basically the profile of the depletion region. As you can see that there is the depletion region is depleted of charge carriers like electrons or holes. However, we are basically having some immobile positively charged and negatively charged ions left behind. And because of this, an electric field is formed from the n-type side to the p-type side, and with maximum electric field at the transition of the p-type to the n-type side. And because of this, an electric potential is formed. So when you are transporting a positive charge from the p-type side to the n-type side, it has to cross a potential barrier. Now when you apply a positive potential across the p-n junction, with the positive voltage applied to the anode and negative voltage applied to the cathode, the potential barrier falls, and because of which it is very easy for the carriers to cross the junction and reach the other side, and this leads to a steady increase in the current. And on the other hand, when we apply a negative voltage to the n-type side and positive voltage to the p-type side, there is an increase in the potential barrier leading to a wider depletion region, and because of which it becomes very difficult for the carriers to migrate across the junction and reach the other side. So this is basically the reverse bias p-n junction. Due to the concentration gradient across the p-type and n-type sides, holes diffuse from the p-type to the n-type side, electrons diffuse from the n-type to the p-type side. The motion of charge carriers gives rise to diffusion current across the junction. The diffusion current is large and drift current is small. the continued diffusion process leads to an extended space charge region on either sides of the junction. This increases the electric field strength and hence the drift current.